Welcome to The Explainer. Today, we're diving deep into a massive shift happening right now. We're looking at how the industry's evolving from AI that just chats with you to truly autonomous systems that actually roll up their sleeves and execute real work.
You know, for a long time, the core limitation of early large language models was actually pretty simple. They were absolutely brilliant at generating text and handling conversational reasoning, but they completely lacked the ability to execute multi-step, real-world tasks. It's like they could tell you exactly how to build a house, but they couldn't physically pick up a hammer to do it. So the ultimate question for developers became, how do we get AI to stop just talking and start doing?
So here's our roadmap for today. We'll start with the anatomy of an agent, move into decomposing complex tasks, then explore the React framework, look at training autonomous agents, and finally wrap up with reflection and self-improvement.
All right, let's jump right into part 1, the anatomy of an agent. Taking a look at the baseline blueprint here, you'll see at the very core is the reasoning large language model. This is essentially the brain of the whole operation. But as we know, a brain alone isn't quite enough to act autonomously. It actually requires 3 really essential supporting layers. First, it needs memory, right? Just to retain past context and keep track of its current state. Second, it needs tools, so it can actually interact with the outside environment. And third, which is really the primary focus of our explainer today, it needs planning. Because without a solid plan, an agent literally wouldn't know what to do next to reach its goal.
Moving on to part 2, decomposing complex tasks. Imagine you're taking on a massive, incredibly complex project. What's the very first thing you do? Well, you'd probably sit down and write out a logical to-do list. And it turns out, AI agents do the exact same thing through a process called task decomposition. For example, if you ask a coding agent to add a brand new feature to your software, it'll take that massive request and split it up into actionable, human-readable steps. Things like clarify the requirements, analyze the codebase, design the feature, implement it, test it, and finally, update the documentation. It literally takes the overwhelming and makes it totally doable.
What's really fascinating here is how the agent bridges that gap between human-like logic and actual machine execution. The LLM maps out these subtasks, and then it seamlessly translates those tasks right into tool selection. So for the step analyze the existing codebase, the agent knows it has to trigger a very specific tool function, something like read_codebase. It's this perfect, direct mapping of a conceptual thought to a tangible utility.
Which brings us to part 3, the React framework.
So before we had these dynamic frameworks, there was actually a pretty big tension in the AI space. On one side, you had reasoning-only models. These use techniques like chain of thought, where they're thinking super deeply, step by step, but they couldn't actually execute any actions. Then, on the flip side, you had act-only models, like toolformer. Now, these could use tools and execute actions, but they completely lacked extended reasoning. And keeping these two functions totally separate, well, it makes it nearly impossible for an agent to dynamically iterate. If it makes a mistake, it just doesn't have the integrated reasoning to course correct.
Enter the React framework, which, as you might have guessed, literally stands for reason plus act. This framework is the ultimate resolution to that tension. It decouples the reasoning and planning, but then tightly couples the reasoning traces and tool actions into this continuous flowing loop with the environment. Basically, it thinks, it does, and then it watches what happens.
The true heartbeat of an autonomous system relies on 3 strict components within this React cycle. First up, you have the thought, where the agent explicitly reasons about its current situation. Second is the action, which is where it actually interacts with the environment using a specific tool. And third is the observation, where it processes the feedback or the result of whatever action it just took.
Let's actually walk through this loop in motion. In the first cycle, the agent's thought is to analyze the existing codebase. So it takes the action to run the read codebase tool. The observation it gets back from the environment reveals that some functionalities are still unclear. Now, right here's where the magic happens. Because of this dynamic loop, the agent doesn't just blindly keep charging ahead to the next step on its old plan. Instead, in cycle 2, it realizes its knowledge is incomplete and dynamically decides on a totally new thought. I should ask the user for clarification. That ability to pivot based on real-time observations, that is exactly what makes the system genuinely autonomous.
All right, let's look at part 4. Training autonomous agents. So how do we train them? Well, one super powerful methodology is supervised fine-tuning, which is demonstrated by approaches like FireAct. Instead of relying on a massive, computationally expensive model to do everything through complex prompt engineering, developers do something really clever. They take successful React trajectories generated by a large model, and they use those as training data for a much smaller base agent. It's essentially behavior cloning. The smaller model just learns by imitating the exact formatting, the thoughts, and the actions of successful past tasks.
But we have to point out an absolutely crucial difference between supervised fine-tuning and reinforcement learning. Supervised fine-tuning is basically imitation learning. The model is just mimicking example data. And while that's really effective, it lacks the ability to explore the environment. That can sometimes lead to suboptimal policies simply because the AI never actually learns how to recover from its own mistakes. And honestly, that's a pretty critical flaw if you're deploying an agent in a high-stakes business environment. Reinforcement learning, on the other hand, relies heavily on trial and error exploration. It actually receives rewards for its actions and actively refines its overall strategy,
which builds perfectly into an active learning process called exploration-based trajectory optimization. In this setup, the agent actively explores an environment, naturally generating both failed and successful paths. By comparing the two using direct preference optimization, it doesn't just mimic success, it fundamentally understands exactly why a certain action led to a failure and it actively learns to avoid it in the future. It's a real game changer.
And finally, Part 5, Reflection and Self-Improvement.
As these agents evolve, they increasingly rely on self-generated feedback loops to continuously improve themselves. A perfect example of this is the self-refine process. It's elegantly simple, really. Think of a human writer drafting a kind of clunky paragraph, reading it back to themselves, and then critically rewriting it to make it better. In self-refine, the LLM generates an initial output. Then it turns around and acts as its own editor to provide feedback, and finally it refines that output based entirely on its own critique.
But we can actually take this concept much, much further with an advanced framework called Reflexion. Reflexion uses 3 distinct, specialized AI entities that all work together. First up, you have the actor LLM. This is your main React brain that's actually executing the actions. Second, you have the evaluator LLM. This is an entity solely dedicated to assessing the quality of the actor's trajectory and giving it a score. And third is the self-reflection LLM. This one deeply analyzes the entire trajectory to generate highly nuanced verbal feedback.
Now, all 3 of these entities come together in the master reflection architecture to perform this incredibly intricate dance. The actor takes an action in the environment, and its trajectory is captured right in short-term memory. The evaluator comes in and scores that trajectory. Then, the self-reflection LLM takes that internal score, pairs it with any external feedback, and creates reflective text. This absolutely crucial insight is then stored in long-term memory, which directly guides the actor LLM on its very next attempt. In a way, the agent literally becomes its own coach.
The whole takeaway here is summarized perfectly by this quote from our source material. Feedback prevents agents from ending up in local minima and provides valuable information on potentially better solutions to pursue. In plain terms, without self-generated critique, an agent just gets stuck repeating the exact same, slightly wrong actions over and over. But with internal reflection, you get a system that breaks out of those ruts and continuously improves itself. That right there is the massive difference between an AI that requires constant human babysitting and one you can truly confidently trust.
Which brings us to a final thought for you to ponder. We've seen how the architecture is fundamentally shifting from models that simply spit out text to intelligent agents that dynamically decompose tasks, execute complex tool-based actions, and intelligently critique their own work to get better and better over time. If they are already capable of this level of true autonomy today, what in the world will they learn to do tomorrow? Thank you so much for joining me on this explainer. Keep wondering and keep learning.